Welcome to Lecture 39, which will be very much a foray into practical matters involving alternating current and direct current and the difference between the two of them. But we'll always have in the back of our mind that important complementarity, much deeper and more philosophical, between electric and magnetic fields, electricity and magnetism, and how that's going to manifest itself when we talk about practical matters involving electric current. Now, so far, most of the discussion I've done of electricity and most of the demonstrations, but not all, have involved DC, direct current, produced, for example, by batteries or sometimes by power supplies that convert alternating current coming out of the wall into direct current. But now I want to focus more on alternating current. And I want to do so for several reasons. First of all, almost all our power systems use AC. And I explain partly why that is. It's partly because we can easily transform AC using the law of induction and transformers, devices that capitalize on electromagnetic induction, to step voltages way up for relatively low loss, long-distance transmission of power. And we've seen in several different lectures how that all comes together. So the power systems tend to use alternating current. It wasn't always the case, by the way. When Thomas Edison introduced the first electric power grid back in the 1890s in New York City, he advocated for direct current, whereas his competitors, Westinghouse and Tesla, advocated for alternating current, and alternating current ultimately won out. And it won out again because of the ability to step power up to higher voltage levels and transmit it with relatively low losses, long distances. When Edison was building a power grid that was in New York City and the generators were right there, DC was fine. But as soon as more and more power was needed and the big power stations were built near Niagara Falls at a very natural source of hydroelectric power, and they had to be transmitted hundreds of miles to New York City, the advantages of AC became very apparent. And so in North America, by about 1900, nearly all power systems were operating on alternating current. Not all, and some lingered on direct current for a long ways into the 20th century, but most had converted to alternating current or were built with alternating current by about 1900. Now, I want to emphasize this is not just about power. It's also about plenty of other alternating currents that are important. For example, the alternating currents that are analogous to audio signals, the currents produced by microphones, the currents that are running through your stereo system when it reads information from a CD or pulls information off the memory in your MP3 player. That's also alternating current. And the same theoretical ideas characterize that kind of AC also. Although I will think about alternating current, be talking about alternating current mostly in the context of electric power. But the basic ideas I'm presenting here will apply in many other cases as well. So I want to begin by figuring out how we describe and characterize AC. And I'm going to use a rather odd term. I'm going to occasionally say an AC voltage. What I mean by that is an alternating voltage, which is associated with an alternating current. But I'm just going to use the term AC, even though it stands for alternating current, to describe either voltage or current. By the way, this power supply that I've used a number of times has on the left a DC power source and on the right an AC power source. So we often need either kind of power. So let's talk about how we characterize AC. So here's a graph showing typical AC voltage. And again, I'm talking about voltage, but this could equally well be a graph of current. So the vertical axis is voltage, the horizontal axis is time, and I haven't plotted time itself, but I plotted the angular frequency, that quantity omega, that describes the number of radians per second. And even though there's nothing circular about this, we can still use that in the context of describing AC. The curve is sinusoidal in shape, and the reason for that, at least in the context of AC power, as we've seen before in talking about how electric generators work, is that electric generators are coils of wire spinning in magnetic fields. We're changing the magnetic flux by changing the angle and therefore changing the cosine of the angle, which determines the flux. The rate of change of cosine is sine, and we get sinusoidal waveforms. So sine wave AC is a natural result of generators produced by rotating coils in magnetic fields. So I've marked several other points on here. I've marked the peak voltage, plus or minus the peak. I've marked that peak, as we found in our calculation on how to design a generator, is about 170 volts here in North America. about 170 volts positive, then it goes about 170 volts negative. There's a kind of average. It's called the root mean square average, and that's 1 over the square root of 2 times the peak, or about 0.707 times the peak, and that's what's actually 120 volts. So when we talk about 120 volts at the power outlets, we're talking about this RMS, this root mean square voltage. If you just took the average of this sine curve, it's up as much as it is down, and so the average, strictly speaking, would be 0. And so the way we average it is to square the whole thing. That makes positive numbers. We take the average of the squares, get an average that is not 0, and then we take the square root of that. And that's where that 1 over square root of 2 comes from. And with a little calculus, you can figure that out. In North America, the frequency of that alternating voltage and current is 60 hertz, 60 cycles per second. That converts to an omega of about 377 radians per second. In Europe, by the way, power is mostly at 50 hertz, and the voltage is about 230 volts instead of our 120 volts root mean square. So it's a sinusoidal variation. If I wanted to write it out, I would write V as V peak, V sub P, sine omega t. So sine is something that varies between plus and minus 1, and multiply by V peak, and we get this peak value at the maximum and minus the peak value at the minimum. The angular frequency, omega, is 2 pi f. The peak voltage is V peak, and the root mean square voltage is V peak over the square root of 2, as I just described. And again, in the lower right are those numbers for your outlets in typical North American power situation. So that's how we describe alternating voltages or currents, with frequency, peak voltage, or root mean square voltage, and we've got the description. But that isn't all. There's something else important. There's phase. There's the relative timing of two AC quantities. Phase is something that is characteristic of two different AC signals, and it talks about when they peak in relation to each other. It's the relative timing. So here I'm showing two complete cycles. For example, a voltage in the brighter color and a current in the darker color, and those two are both peaking and having troughs, but they're having them at different points. And in this case, you'll notice that the current, the darker curve, has peaked before the voltage. In fact, it's peaked 90 degrees, a quarter of a cycle, pi over 2 radians. Those are all ways of saying the same thing, before the voltage. We're very interested in the phase relationship between current and voltage in AC circuits. The voltage here is V peak sine omega t. Its phase is 0 in the sense that it starts rising right at time equals 0. The current in this case is I peak sine omega t plus some phase angle, which is given the lowercase phi, not to be confused with magnetic flux. And so in this case, the current leads the voltage by pi over 2 radians, which is 90 degrees, or a quarter of a cycle. Why are we interested in this? For a lot of reasons. First of all, if I were to calculate the average power in this particular situation that's shown here, I would see sometimes when the voltage was positive and the current was negative, and the power would be negative. And that means during that time, the circuit would actually be giving back power to its source. Other times it's positive. And if you work that out over the whole cycle, you would find that this particular situation is one in which there is no net power consumed over an entire cycle. If you want to send power, you have to have voltage and current in phase. As soon as they slip out of phase, you're sending less power for a given current than you could otherwise by having them in phase. And that plays an enormous role in some major power failures. For example, the 2003 power blackout that left 50 million people in North America without power, some of them for several days, was caused in part by current and voltage getting too far out of phase, and to supply a given amount of power, the current had to be larger than it should have needed to be, and a wire overheated and sagged and touched a tree and triggered a whole sequence of failures that cascaded through the system. So phase is really important in AC systems. Why would things get out of phase like that? Why would they get out of whack? Well, they would because of the presence of either capacitance or inductance in a circuit. And I want to look at the role that capacitance and inductance play in alternating circuits now. And then we'll do a little demonstration of that, because they play a profound role in establishing these phasings, and taken together, that complementarity between capacitors and inductors, between electricity and magnetism, gives rise to some new phenomena that are really important in electrical engineering, radio engineering, things like that. So let's look first at resistors, because resistors are the simplest kinds of components. We understand those in all their detail. We understand the relationship between current and voltage in a resistor. The relationship is given by Ohm's law. It says the bigger the voltage for a given resistance, the bigger the current. The bigger the resistance for a given voltage, the smaller the current. We know Ohm's law. Ohm's law is a direct relationship between voltage and current in a resistor. So in the little circuit I've shown here, I've got an alternating source, and the symbol for an alternating source of voltage or current, is a circle with a kind of sine wave in it that takes the place of a battery in this particular circuit. And in this utterly simple circuit, the source of alternating voltage is connected across the resistor. The resistor current and voltage are in phase. That's what that equation says. It says at any given instant, the current is the voltage over the resistance. If the voltage is at its peak, the current will be at its peak. If the voltage is going through zero, the current will be going through zero. If the voltage is at its most negative going value, the current will be going in the opposite direction at its greatest magnitude. So there's a picture of that. Two sine waves, one representing current, one representing voltage. They're perfectly in phase. Their peak values are related by Ohm's law, as are their values at any given instant. That's the picture for resistors, and there's no big surprises there. Now let's move on to the other components that we know about, capacitors and inductors. And we'd like to sort of characterize them the way we do resistors, but we can't quite because they have different relationships. The fundamental defining relationship for a capacitor is its capacitance is charge divided by voltage, or rewritten Q is CV. There is not a direct relationship between current and voltage in a capacitor. There's a relationship between charge and voltage in a capacitor. So here's a circuit with an AC source and a capacitor. If I take the rate of change of that equation, take the rate of change of the left side, rate of change of charge on the capacitor. Well, where's the charge come from? It comes flowing along the wires coming into the capacitor. It's carried by the currents. And so the rate of change on the capacitor plates, rate of change of charge, is the rate at which charge is flowing through those wires, and that's simply called current. So if I take the rate of change of this equation at the top on describing a capacitor, I have I, that is delta Q over delta T, is C delta V over delta T. So the equation that describes a capacitor's current-voltage relationship involves time. It says the current is proportional to the rate of change of voltage rather than a direct relationship between current and voltage. Because a capacitor is not a resistor, it does something different. Now, it takes current to move charge onto a capacitor. And what that means is that current has to start flowing to a capacitor before the capacitor can build up voltage, because the voltage across a capacitor is proportional to the charge. You can't get charge on the plates before you've had some current flowing. We saw that in that simple resistor-capacitor circuit that we looked at here on the big screen before. With the oscilloscope, we started with zero voltage, and it took a while for the voltage to build up as current flowed onto the capacitor. In AC circuits, that manifests itself by the fact that the current leads the voltage by pi over 2 radians, or 90 degrees, or a quarter of a cycle. Again, those are all ways of saying the same thing. So there's a picture, this is in fact the picture I showed before, of current and voltage in a capacitor. And when I say current in a capacitor, I'm being a little loose. No current flows between the insulated gap between the plates of a capacitor, but current does flow in the wires leading to the capacitor, and I call that the current in the capacitor. So there's that relationship. The higher the frequency, the more rapid that charge movement back and forth to get charge on and off the plates, and therefore the higher the current. And I'm not going to prove it in rigorous detail, but in fact the peak current is the peak voltage divided by this quantity 1 over the frequency times the capacitance. So the capacitor acts a tiny bit like a resistor with resistance 1 over this quantity frequency times capacitance, and that quantity is called the capacitive reactance. But I want to emphasize that that quantity is not the same as resistance, because that doesn't tell you the whole story. The whole story is there's also this phase lag introduced by a capacitor in which current leads voltage. Now let's move on to inductors. In inductors, as we've seen in the previous lecture and from Faraday's law, the voltage is the inductance times the rate of change of current. So this is again a complementarity between inductors and capacitors. Voltage is now related to rate of change of current. In the capacitor, current was rate of change of voltage. So the induced voltage arises as soon as the current starts to change. As soon as you try to change the current, it was initially zero, you try to build it up, you get voltage immediately. So the voltage leads the current in an inductor, and it does so by pi over 2, or 90 degrees, that is a quarter of a cycle. So there's the picture for an inductor. The voltage has peaked, 90 degrees, a quarter of a cycle, pi over 2 radians before the current has peaked. And there's the circuit with the voltage source on the left and the inductor, again symbolized as a coil of wire. The higher the frequency, the more rapidly the current is changing, and the bigger that back voltage that tries to keep the current from changing, and therefore the smaller the current. So it's the very opposite of a capacitor. An inductor has a peak current, in fact, which gets smaller as the frequency gets bigger. An inductor sort of acts like a resistor, a frequency-dependent resistor, with its resistance in quotes equaling the frequency times the inductance. And again, I put that in quotes, and I remind you that this is not the whole picture. The whole picture of what the inductor does is to limit the flow of current in a frequency-dependent way, but also to introduce this phase lag. So that's what an inductor does. And let's now pause and look at all three of these circuit components, resistors, capacitors, and inductors, all together in one table. So here they are, resistor, capacitor, inductor. At the top, I write the defining relationship, which tells you what kind of electrical component something is. A resistor has this direct proportionality between voltage and current. Capacitor, it's between charge and voltage. Inductor, it's between magnetic flux and current. The current voltage relationship for the resistor is the same. It's Ohm's law. I just rewrote it as I equals V over R. For a capacitor, as we saw, it's a relationship between current and the rate of change of voltage. For an inductor, it's the relationship between voltage and rate of change of current. Phase, in the resistor, voltage and current are in phase. In the capacitor, the current leads by 90 degrees. In the inductor, the voltage leads by 90 degrees. And this quantity, the reactance, the thing that's sort of like resistance, well, for the resistor, it is the resistance. For the capacitor, it's 1 over frequency times capacitance. So the lower the frequency, the bigger the reactance, the harder it is to get current in a circuit with a capacitor. The inductor is the opposite. The inductive reactance, X sub L, is omega times L. Okay, so that's a look at these three things individually. What happens now if we put inductors, capacitors, and resistors all in a circuit? I'd like to show you what happens. Well, before we do that, let's look at a real problem. So here is a circuit in which we've got a resistor, an inductor, and a capacitor, and some source of alternating voltage. And I want to ask the question, at what frequency, omega sub D, called the driving frequency, because it's driving this circuit, making current happen in it, will the current in this circuit be the greatest? Now, this is a series circuit, so the same current flows in all three components, as we know. We know that the inductor voltage leads the current by 90 degrees, and we know that the capacitor voltage lags the current by 90 degrees because the current leads in a capacitor. What that means is the voltage in the inductor and capacitor are 180 degrees out of phase. When one peaks, the other is at its bottom. Why? Because they've got the same current in them. The current in the inductor, the current in the capacitor are the same because they're in series. One of them, the voltage leading by 90, one it's lagging, and consequently, we get a pattern that looks like this, with the voltage, say, in the inductor. In this case, I've shown it bigger, but it doesn't have to be, and the capacitor. And notice that they tend to cancel each other out. When will they cancel each other out exactly? When their peak values are the same. Well, V peak is given by this Ohm's law-like relationship, the current peak times this thing, the reactance. So they're going to cancel when the inductive reactance and the capacitive reactance are the same. That is, when omega L, the inductive reactance, is 1 over omega C, the capacitive reactance, and we can take that expression. That's what will give us this situation of complete cancellation, and we can work on it algebraically, multiply by the omega, divide by the L. Omega squared is 1 over LC, and omega is 1 over the square root of LC. That's the frequency at which the current will be a maximum. At that frequency, it's called the natural frequency, omega naught, 1 over square root of LC. At that frequency, the inductor and capacitor voltages have canceled out. And as far as the generator is concerned, it's just a circuit with a pure resistance. It isn't really, but that's how it behaves in this case. So there is our answer for the natural frequency at which things happen in this RLC circuit. We get the maximum current. It's determined entirely, in this case, by the resistance. Let's pause and look at a real-world demonstration of that phenomenon. This phenomenon we've just looked at theoretically, whereby the current is a maximum with a particular combination of capacitance and inductance, should remind you of something we talked about in Lecture 17, namely resonance in mechanical systems, whereby if a system was driven at just the right frequency, it would develop large-scale oscillations, which could have disastrous consequences. The same thing happens in electrical circuits. We use this idea of large response near or at a natural resonant frequency, in this case the large response being a current. We use it for tuning circuits in electrical devices like radios, televisions. In the old days, tuning a radio, as I mentioned before, was literally turning the shaft of a variable capacitor and adjusting the capacitance in a circuit containing both a capacitance and an inductance. Today we do it by more sophisticated means, but it's still the same idea. The inductance and capacitance set a frequency at which the circuit has the greatest response. It turns out the sharpness of that resonance depends on how much resistance there is in the circuit. So I have a demonstration of that here. Here's our oscilloscope that we've used before. Again, it's a voltmeter that displays voltage as a function of time. Thanks again to Agilent Technologies for providing both the voltmeter and this device, which is a so-called function generator. It's set to produce a sine wave, and right now it's producing a sine wave of 2 volts peak to peak. It means between the peak voltage and the lowest voltage it goes to negative is 2 volts. And it's set to produce it at 800 kilohertz, 800,000 times per second. This thing is oscillating. That sounds awfully fast, but it's pretty low frequency by today's standards. And you see on the big screen and also on the oscilloscope a sine wave displayed. And that is the sine wave that represents this particular waveform that I'm generating here. As always, we have an awful lot of noise in this studio, so that sine wave doesn't look nearly as clean as it ought to. I'm also not taking precautions and shielding my wires like I should. Now, what I have here is an inductor, a capacitor, and a resistor. And the value of the inductance and capacitance are chosen so that the resonant frequency, this natural frequency this circuit wants to go at, the frequency at which the effects of the capacitor and inductor cancel each other out, is somewhere in this range that makes it reasonable to start at 800 kilohertz. So now I'm going to bring the frequency up. And you see that on the screen because the peaks of the sine wave are getting closer together. Remember, the horizontal axis is time. And so as the peaks get closer together, the time between cycles is less and the frequency is therefore greater. And you'll notice something else happening. You'll notice the amplitude growing as the frequency increases. Now I'm at 1300 kilohertz, 1.3 megahertz. It's going up, it's going up, it's going up, it's going up, it's going up. It continues to rise, and the frequency continues to get higher and higher. There it is. It's about peaked now at just about 1440 megahertz, 1.44 megahertz, 1440 kilohertz. By the way, that's very near. That's near the upper end of the AM radio band. You may have an AM radio station at 1440. It is a frequency that's used for AM radio. So this is the carrier frequency of a common AM radio frequency. And as I go higher, you see the amplitude dropping again. So there's the resonance as we tune through that frequency of about 1440 kilohertz, 1.44 megahertz. We see the current, which is, I'm measuring that current by measuring the voltage across the resistor because the current and voltage in a resistor are in phase and are proportional. So there is the resonance peak occurring in that circuit. This is a resonant circuit. This particular circuit resonates at that frequency of about 1440 kilohertz. That's the natural frequency it would like to oscillate at. So that's a resonance effect. Let's do an example of understanding how we use this resonance frequency to tune a radio. To do that, we'll have to turn off our oscilloscope display and go back to our usual display with the big monitor. So let's do a quick, simple calculation that illustrates this idea. FM radio. We've got an LC, inductor capacitor tuning circuit. The inductance is 200 nanohenries. The frequency of FM radio is 88 megahertz to 108 megahertz. We've got a variable capacitor like I showed you with rotating plates. What range of capacitor is needed? Well, the frequency is 1 over the square root of LC. That's the frequency the circuit wants to go at. That's the frequency we want to be able to range from 88 to 108 megahertz. That tells me omega squared is 1 over LC. That solves for C. C is 1 over L omega squared. Omega is 2 pi times the regular frequency that we talk about, f, the cycles per second. So I can write C as 1 over L, and then I substituted 2 pi f for omega. Squared it because it was squared up here, and we do the numbers. At 88 megahertz, work all those numbers out. You get 1.6 times 10 to the minus 11 farads. That's 16 picofarads. Do the same thing at 108 megahertz. You get a smaller capacitance because it's a higher frequency. That's 11 picofarads. So in this case, you need an 11 to 16 picofarad capacitor. So there we've been electrical engineers, and we've designed the tuning circuit for an FM radio. Now let's look at a few more applications of this idea of resonance in LC circuits. Here's another example. This is the crossover network in a loudspeaker system. In any good loudspeaker system, there are at least two separate loudspeakers. One a tweeter for high frequencies, one a woofer for low frequencies. Sometimes there's a mid-range as well. We use inductors and capacitors to steer the low frequencies to the woofer and the high frequencies to the tweeter, so we don't waste low frequency power trying to drive the tweeter and high frequency trying to drive the woofer. And how do we do that? We use inductors. Inductors pass low frequencies without much so-called resistance. They don't have much reactance. They let low frequencies through. Capacitors let high frequencies through. And so this simple circuit shown on the right drives these two different loudspeakers, the small tweeter that responds well to high frequencies and the big woofer that responds well to low frequencies. And on the left, you see how both these speakers work. They involve a coil wound around attached to a moving flexible cone. The coil is around a magnet but not attached to it, and the coil moves back and forth with magnetic forces as audio frequency currents run through it. So there's an application of this idea. If we simply take a capacitor and inductor and connect them together and charge up the capacitor will discharge through the inductor will build up magnetic energy, and the whole thing will result in a cycle of so-called LC oscillations. And that's in fact what we do in a radio transmitter. We feed an LC circuit with appropriate energy at the right times because there is some loss, partly the loss we want of energy off into radio waves and partly energy lost in resistances. And you can see in this picture as you go around the cycle, you start with an electric field in the capacitor. You build up current in the inductor as the capacitor discharges. Eventually, you've got all the energy stored in the inductor as magnetic field energy, but the current can't stop abruptly, and so it goes around and around and around. And if you do a mathematical analysis, you'll find that this thing undergoes sinusoidal oscillations. And those oscillations have frequency, the same as the one we just developed. Omega is 1 over root LC. The frequency is 1 over 2 pi root LC, and the period is 2 pi root LC. Those are all related. This should remind you of a mechanical system, a mass spring oscillator that we talked about way back in the mechanics section. It's analogous, and the mechanical analog is this. Here's a mass spring system. The spring has spring constant K. The capacitor in the LC circuit corresponds to the spring. The current corresponds to the velocity, and the inductor, which provides a kind of inertia resisting changes in current, corresponds to the mass m. So there's a perfect mechanical analog. The difference is we can make a much broader range of oscillations electronically than we can mechanically. So a whole range here of practical ideas using the way capacitors and inductors behave complementarily with these frequencies of oscillation, in this case being set by the inductor and capacitor in one case and by the mechanical system, the K, the spring constant, and the mass in the other. But let me summarize. We've discovered that AC voltage and current are characterized by their amplitude, expressed either as peak or RMS, their frequency, expressed either as this angular frequency or more commonly as regular frequency in hertz, their phase. Capacitors and inductors introduce different phase differences, and by exploiting those phase differences complementarily, that leads to the resonance in RLC circuits and to these natural oscillations in LC circuits. Well, that's the end if you're like to be done at this point, but if you'd like to do a little electrical engineering, let me give you a challenge. So here's the challenge. I've got a circuit in which I have a capacitor of 20 millifarads on the right, a capacitor of 5 millifarads on the left, and a 100 Henry inductor. And I've got two switches, A and B, and right now they're open. So let's charge the 20 millifarad capacitor to 50 volts. I'd connect a 50-volt battery across it and then disconnect it. And I'm going to ask you to figure out how and when you would close and open the switches to transfer all the energy from the larger capacitor so it ends up in the smaller one. And when you're all done, what will the voltage be on that smaller capacitor? So think about that challenge, work on it. I'll come back with the solution. Okay, here's the solution. what you have to do is close switch B and leave it closed for a quarter of a period. Remember that cyclic diagram. A quarter of a period later, after that capacitor had all that energy stored in its electric field, all the energy will be in the current flowing in that inductor. It will be stored in the magnetic field of the inductor. So I close switch B and I leave it closed for a quarter of a period. All the energy is in the inductor. A quarter of a period is a quarter of 2 pi root LC. In this case, that comes out to be 2.2 seconds. So you close switch B for 2.2 seconds. Then you simultaneously close A and open B, and you keep A closed for another quarter of a period, only now it's a different quarter of a period because it's the LC system of the 5 millifarad capacitor and the 100 Henry inductor. And you then open switch A, and at that point, all the energy will be stored in the electric field of the capacitor. That period is different because we've got 5 millifarads instead of 20. You might say, why isn't it 4 times different? It isn't because of that factor of the square root that appears in those formulas. And so you wait another 1.1 seconds, open switch A, and you've got all the energy that was initially in the right-hand capacitor, the 20 millifarad capacitor, now stored in the 5 millifarad capacitor. And you did it with the intermediary of energy storage in the magnetic field.